Good afternoon. We start limits. What we're going to do first is just kind of intuitively go over what a limit is. At the end of the unit, I will give you the precise definitions, the actual mathematical definitions. Right. In a sense, what a limit is we would write this here, right? The limit as x approaches a of f(x) equals L. What that means is the values of f of x are approaching L, they're getting closer and closer to L, as the values of x approach A. Now, the easiest way to look at it is look at a graph. Just trace from both sides as x gets closer to your value A. If f is approaching some value, that's the limit.
All right.
You're good. Right, so this notation is important. That's the notation we're going to be using a lot. And I'll probably also be using the shorthand notation, which is just a right arrow. Right, so I'll just go f(x) arrow L means that's the limit. We also have the one-sided limits from the left and from the right. So again, just notice the notation. A raised to the power of a negative sign means you're approaching A from the left side of A. So all your values are less than A. If it's a plus, that means we're from the right of A, so all of your values are greater than A. And there will be a theorem later, but your limit exists if and only if your two one-sided limits are the same. Right, so you're approaching the same value from both sides, then your limit exists. But notice in the previous step, that was weird, okay. Notice in the previous definition, it says x is not equal to a. What the function does at a is irrelevant to the limit. We just care about how the function behaves around a. F(a) could not exist and still have a limit. Right, and then of course it's also possible that the function is infinite. Right, either it continues to increase without bound or decreasing without bound on either side of a. And that's where we use the notation of positive infinity and negative infinity. Again, important to note, infinity itself is not a value. It's a concept. So technically speaking, this does mean the limit does not exist. We're just being more specific and saying why it doesn't exist. It's because it's either increasing or decreasing in value. What's up there is for the left-hand side, this is for the right-hand side. And then obviously, if both the left and the right either increase without bound or decrease without bound, then we'd say the overall limit is either positive infinity or negative infinity. Which is mentioned there. With the notion now of limits, we can formally define a vertical asymptote. You should have touched on it in pre-calculus.
So like a line approaches a point that actually never touches that point.
It actually can touch that value on one side. Say there's our vertical asymptote. Still a vertical asymptote, but it is actually touching on it. How common is that from the pre-calculus functions? Not common. But there are functions that exist that can do that. Piecewise function is the easiest one to come up with. Right, but you're at least familiar with the notion of a vertical asymptote. That's the formal definition. And it involves limits. Right, so what either of the one-sided limits is infinite, or they're both infinite. In mathematics, or is not exclusive, it's inclusive. If I say A or B, that also means or both. Of course, there will be some circumstances where it is an implied exclusive, like positive infinity or negative infinity. It is not possible to be both. Right, so this is a case where the right-handed limit would be positive infinity, right? But the left-handed limit isn't, but it doesn't matter. Because it only has to be one of those three that has to be true to be a vertical asymptote. Ooh, okay, something's missing. I think somehow my animations get out of order again. Which is really annoying, but that's it. So two important limits. Limit as x approaches a if x is just a. That is not difficult to see. Limit of a constant is just that constant. Again, that's not terribly difficult to see. I'll be coming back to those next time.
You post these slides, right?
They're already up there. I generally get them up there that morning.
Okay.
So this is what I was saying earlier. Limit at A exists if and only if the limit is the same on either side. Right, if you think of it in terms of graphs, that is really obvious. Let's say that this is my value A. That would be some point AF of A, right? Whatever happens to be. A, it's approaching f of A, right? Coming from the right of A, it's approaching f of A, therefore that's your limit. Let's pretend instead it's open there. So that point no longer exists. Let's call that value down there B. Why not? I did the wrong one. It's actually here, right? This case, the two one-side limits are both B, right? As we come in from the left, what are the y values approaching? They're getting close to that value B. Same thing from the right. So the limit would be B, even though that point is not defined, the value is f of A. That's why I said, what the function does at your point doesn't matter. It's irrelevant for the limit. All that matters is the neighborhood. So here's that function now.
And because they're both approaching that same undefined point, it's still considered a
Yes. So again, yes, that point itself is undefined, but they're still approaching a value.
and it's the same one.
It's approaching the B value. So that would be your limit as x approaches A. This idea will be important later, that those are not the same. But for limits, it's irrelevant. Again, this is going to be our A value. I don't know what to call this. That's clearly A f of A, right? That's a closed point. Up here, we'll say it's B. As we're coming in from the left now, we approach f of A, right? But now as we come in from the right, we're approaching B. That limit does not exist. Because you're not approaching the same value from both sides. Right? It's not coming together. Your one-side limits both exist, but since they're not equal, your limit itself does not. Okay, so these are also pretty important limits. Limit as x approaches A, 1 over x minus A to the n is positive infinity if n is even. If n is odd, then the limit itself does not exist because your one-side limits will be doing something different. From the right, it'll be going to positive infinity. From the left, it'll be going down to negative infinity. All we're going to do today is estimate limits, both graphically and numerically. Graphically is pretty straightforward. You just look at a graph. And you kind of guess, oh, what does it look like? It's approaching. Remember, you cannot ever say for certain what that point is because graphs are not assumed to be drawn to scale. If I give you a grid on the graph, then yes, you can say, oh, it's definitely that. If it matches up on that cross, right? Otherwise, it's just a guess. The second method is numerically, and that is second method is numerically. That is done by creating a table of values. Right? You take values on the left side of A, and you say, okay, so what does that equal for those values? Values on the right side of A, what is F for those values? And determine the limit. If they seem to be going to the same thing, that's your limit. Again, that is always just numerical. It's still just an estimate. Because what it does at A is irrelevant. Right, and that is this process. All right, so you create your table of values. So it could look something like this. I generally do not split it into two separate tables. I generally do a horizontal table. Have my left values of A, my right values of A. And then C, are they going to do the exact same thing? That's typically what I do. It's looking at your values, right, and basically trying to determine, are they approaching the same Y value? And then you can confirm it. I think that's by looking at a graph. So clearly there's an issue with the graphical method, and that is you need the graph. Right? So before technology, if I gave you some really ugly looking function, like x to the sine of the natural log of x, what's that graph look like? Without technology, you have no idea what it looks like. So the graphical method's not really that good. But of course now we have technology, so we can just plot the graph. So I believe there's a mix of problems in the examples. Some that require tables, some that I think they give us the graph or some. For the ones with tables, I'll probably also go ahead and give the graph. We'll generate the graph as well to confirm our numerical guess. Estimate using a table. This one will use the calculator. For the next table one, I'll actually show you how to generate the table on Wolfram. We need an x, we need an f of x. Values to the left of 3, but keep in mind that for the limit, you still want to be close to 3. .9, less than 3 and still pretty close, right? But we can get closer. .99 is even closer. And then 2.999 is even closer still. And I know for this problem that's going to be good enough. And typically what I'll do is I'll just put a 3 there, even though I don't care about it, just to separate them. To the right of 3, we want values larger than 3, but still relatively close. 3.1, but we can get closer. But we can still do better. And this is just the way that I do my tables, because now you'll be able to see, right, we'll be coming in from the left, coming in from the right, and are they approaching the same value? It's just easier to read that way. There is an advantage to the other way of having 2 separate charts, and that's if you need more data points. Right? There are going to be some functions where that is not enough to give you a conclusive answer. So you may have to go even further. But this one's pretty straightforward. So assuming you have the Inspire CX2 CAS, turn it on. For the first time, you come to the home screen. Scratchpad is good enough. Here's the easiest way to do it. Define your function first. So to define, you want a colon and equals. So you say control, and then it's right above that button there. Then the function. What was it? X squared minus 9. X minus 3, and use parentheses correctly. Enter. F is now stored as a function of x, which now allows me just to do this. F of 2.9 is just 5.9. There's 2.99. And 2.999. So I'll just, oops. I will just quickly fill in the chart and then come back to the calculator. F of 3.1. .01. .001. Right. That method obviously has the advantage of you don't have to keep writing in your value for x each time. If you just store the function, you can just recall it. Again, I'll just fill those in and then switch back to it. And again, what it does at 3 is irrelevant. By the way, what is it at 3?
Undefined?
It's undefined. It's 0 over 0, which is undefined. But the limit does exist, right? What's the limit?
6.
The limit is exactly 6, but for our purposes right now, what we can say is it appears to be 6. Which means there'd be a hole at 3,6. Because at 6, the function itself is undefined. Or at 3, rather, I'm sorry, the function itself is undefined. Let's just say 6. And we can quickly confirm that. So you can either use the middle, acts as a mouse pad to scroll your mouse cursor up to here for the graph, or easier way is just hit Control-0. Let's plot the function. Of course, there is a problem. The calculators do not plot holes. So you just have to keep that in mind. Let's go ahead and trace the graph. Remember, we're going to 3, right? At 3, it's undefined. Nice, it actually does tell you that. That's nice. But it looks like, right, if you look at the y values, they're approaching 6. And the graph itself is connected, which means that it's going to do the same thing from the other side. So that confirms our guess. You want to estimate the limit as x approaches 1 of f of x and compare it with f of 1. Well, these are grid lines, so it's going to be pretty good. But we're approaching 1. Since we're given a graph, let's look at the left-hand limit first. I'm just going to write equals. I'm too lazy to do anything else. I guess I could do the squiggles. Here's x equals 1. Trace it. What value does it appear to be approaching? 2. 2.0. Do the same thing from the right. Appears to be approaching 2 as well, right? Means our limit appears to be 2. But what does f of 1 look to be?
3.
I don't know if they went over discontinuities in pre-calculus with you. I believe they should. And they should classify several types. You remember what those types are? jump, infinite,
Removable.
and removable. Which one's this?
Removable.
This one's a removable discontinuity. This limit, numerically, so using Wolfram, let me just generate the table. First, I'll go ahead and define f of x. That underscore is telling Wolfram that x is the independent variable. Colon equals, now type in the function. Again, use parentheses. 5 plus x. Notice that the s is capitalized in square root. What happens if I just do a little s? Notice the text is now blue. That means that it's reading SQRT as a string, not a function. So that's a really good way of looking, do you have the function right now, right? There is f of x. Let's first create a table from the right. If I do this, this is a comment. It will not actually execute as part of the code. I think I said right, let's do left first. Going to do table form and then have it create a table. What are the columns? X and f of x, right? What am I using as my table variable? X. There are several ways now to proceed. I could give it a starting value and then give it a rule. So I could say, yeah, let's start at, we're going to 0, right? Yep. Okay. Could start at -1 and tell it to decrease by a certain value each time. It's not really what I want. I want it to be specific values. I will now list out what those values are. That's all I need for the table. So let me show you what's going to happen if I just do the table. So to execute it, you don't hit enter. Enter just moves you to the next line. Shift, enter. Doesn't look like a table. That's why I do table form. Possibly one better. Because there's an option in table form. Table headings. Hyphen, and then that is the less than sign will automatically form an arrow. I think it's going to be this. First, just make sure that's right. This one. The first set of headings will give you row. Second set of headings will give you the columns. And anything inside quotations, it reads as just text. Is that good enough? Looks good. So I'll say, there you go. There is our table for the values approaching 0 from the left. I'm going to copy that as an image. Of course, you're going to cut off, so I can't do that. I'm going to have to do it this way. Convert to image. And it's still cutting it off. I don't like that. Let me re-execute that. I'll have to do it. Oh, oops, deleted. Those for some reason. I'm going to cheat. Copy paste. Coming in from the right now, but it's 0, isn't it?
Yeah.
So instead of rewriting the whole bloody code, I'm just going to copy paste and then just make the minor changes I need. And that appears to be good enough, right? So what does the left-hand limit appear to be?
0.2236.
What about the right?
The same.
Does the limit exist? Yeah, about that probably.
Are we going to be tested on our use of Wolfram? Or is that just another?
Possibly. It obviously won't be on the in-class exams, but on the online tests, I may require you to use Wolfram.
But when we have Wolfram, will we always have a calculator that we can also use?
You'll always be allowed to use a calculator.
Okay.
Approaching 0 from the left. What is g of x approaching?
2.
Looks to be 2, right? If we come in from the right now, what does it appear to be? Does the limit exist?
No.
So we just write the NA. Does not exist. What is g of 0?
-1.
What kind of discontinuity would that be? That's a jump discontinuity. Yay, trig. Simple trig, though. I think for this one, I'm going to use the calculator for a specific reason. Sine, right? So trig, and I just found out if you keep clicking it, it goes through all of the possible values. So we just want sine, right? Sine of 4x divided by x. Here's why I want to use the calculator, which you should be familiar with. When using a calculator to evaluate trig functions, what do you have to be aware of?
Right.
What are radians? You're thinking. It's a unit of measure. Specifically, it's the standard unit of measure for an angle. Are radians the only unit of measure?
Right.
Radians and degrees are your two, right? Yep. They're the two most commonly used. There's actually other ones. Better make sure your calculator's in the right mode.
So, we're all right.
What's the rule? You're dealing with angles. It's always radians, unless it's otherwise specified. For calculus, it's going to have to always be radians whenever you're dealing with the function itself. And so if you want to find limit of a function, your values have to be radians. When we get to derivatives, are always in radians. Well, the TI, Inspire, it's very easy to tell if you're in the right mode.
It's right there, right?
Yep, top right corner, next to the battery. It tells you what the mode is. It's even better. If you want to change the mode, I can just scroll over to it and click it. You don't have to go through those nasty menus. If you don't have it Inspire, I'm so sorry. So now we have at least the right mode. We were approaching 0. So there's negative 0.1. Enter. No, it's not where I want this to go. 0.01. Negative 0.001. Is that kind of giving us a conclusive answer?
Yeah. I would do one or two more.
Here's before from the left. And we did 4 on the other side, so we're going to have to do it here too. Does that seem pretty conclusive? What does it appear to be?
4.
4. I'll just go with 3, I guess, or 4, 3.89. Does the limit exist?
Yeah.
What does it appear to be?
4.
Be careful because we can only say 4 with that kind of certainty because of how I rounded the table. X squared is 2x divided by x equals 2. And the limit was approaching 2. Let's just start with those 3. Change these, so 2.1, 2.01, 2.001. Execute the whole thing at once. It should give me 2 tables. Right. Is that good enough? Is that conclusive? Yay, technology. What's his limit appear to be? 2? Appears to be 2. Let me use this one to now show off plotting. Plot. Real quick. What's that called? I'm not talking about this coming, I'm talking about what is that image?
Graph.
That's what they tell you, right? It's not a graph. Graph is something completely different in mathematics. This is a plot. So I'll be using the plot terminology a lot. A graph is a set of edges and vertices in mathematics. In fact, there's a whole branch called graph theory. You've actually been lied to a lot in your math classes. I'll probably share some more of the lies as the semester moves on. So we're plotting, I already have f of x defined, so I'm just going to use f of x, but you just put in what you want the plot of. You now need a domain. So what values of x do you want? I mean, we're at 2, so I could just do 0 to 4. And that is really all you need. You have to enter, and there you go. There are other options that I'll probably get into later in the semester. For my purposes right now, this is good enough. Again, notice what it's not showing. It's not showing the hole at 2. Because there's a hole at 2. It's undefined. But again, it's good enough. Actually, there is something I do want to do. I want to put on grid lines. Maybe I'll just do automatic. See what that gives me. Oh, that's right. I'm used to the desktop version. Oh, that works. Except it shrunk it. I don't know why it shrunk it, but yeah. We'll make do. Because I can just do this. That's what I want. Picture. Yes. Victory is mine. So approaching 2, we go from the left. Right, so we trace up this way. What do we appear to be approaching? What y value? 2. Right, come in from the right-hand side. What do we appear to be approaching? 2. We've confirmed our result. Notice I say confirm, not prove. There's a difference. I can't actually prove it using the graph because it's not drawn to scale. But we can visually confirm it. Same thing, by the way, in science. Science, you never actually prove anything. All you do is confirm stuff. So for instance, the law of gravity, gravity's never actually been proven. It's only been confirmed. I'm not mistaken here, the last 2 are plots given. What does that limit appear to be?
4.
But what's h of 2?
1.5.
Yeah, I'd say it's probably about 1.5. That's a discontinuity, what kind?
Removable.
That's a removable one. Again, you can easily tell just from looking at it. Oscillates, right? Now, the really cool thing about sine of 1 over x no matter how far you zoom in around the origin, its shape is the same. It's just the frequency decreases or increases, right? So they just get faster and faster and faster, but otherwise the shape is exactly the same. And of course, obviously, the further out you get, it becomes like really stable. Right, so this is what your heartbeat looks like on the test deck. As you get to zero, the closer you get to zero, the closer the actual test time is in your heart. Until eventually maybe it'll just flatline at the end. By the way, it's not an excuse not to take the exam. So if you flatline, you get a 0 on the exam. It's not an excuse. It would be unfortunate, wouldn't it?
Yeah.
Maybe I'd make you do a makeup test and I'd have you do the calculus of the flat line. What does this limit appear to be?
0. Here.
This limit does not exist. Because it keeps oscillating between positive and negative 1. And clearly at 0, the function itself is undefined. Right, so notice it's never actually stabilizing out to anything. It keeps bouncing between negative and positive on both sides. So the limit does not exist. Intuitively, that is what the limit is. Are there any questions on the limit? This is all well and good. But again, what if I give you a really ugly looking function, like when I started with x to the sine of log of x? And I say, what is that limit as x approaches pi?
I just wouldn't be happy with it.
And I don't want an approximation either, I want the exact value.
And I really wouldn't be happy.
You start to see where this problem arises.
What is continuous at that point at least? So you can just plug it in.
We haven't gotten to that point yet.
Oops.
I'm leading to that. Taking 3 points away from your score because you ruined my fun. So joy. All right, this method isn't really good for that. Because I'm pretty sure, even to get accurate to 4 decimal places, you're going to need quite a few data points on either side. And that's only 4 decimal places, which is garbage precision. Generally speaking, I want at least 10 to the minus 9 precision, which is nano units, which is going to take even more. But that's okay, because it's calculus, and we actually have methods of finding exact values. That is our goal, is to look at, okay, well, how can we actually exactly find it analytically? Right, so using algebra. Even a lot of those functions don't work either. You have to use L'Hopital's rule. But we'll get there too. But for now, that's what we're doing with limits. So for right now, don't forget to return your agreement form. Also, the section 2.2 homework on WebAssign will be due the 11th, before class starts. So I'll always give you 1 week when I cover it. I do not think our roster has changed that much. So get into the groups that you formed last class. Anyone who's not here last class, we'll just add you to a group. But first, form the groups that we already formed. I actually do have the index cards this time, so we'll get to them. Wow.